Hello! So, in this video we're going to be talking about the absolute convergence of integrals, not to be confused with sequence and series and things like that. So, suppose that we have some function f. It's defined on the closed A to open B, going to R, with B being something possibly infinite, right? I have less than or equal to infinity, meaning it maybe goes on the infinite ray. And, moreover, let's assume that f is Riemann integrable from A to C for any C between A and B, where here I have equal to B if, so I guess I shouldn't have equal to B, for anything less than, sorry, B. There we go. And finally, let's assume that f itself is absolutely convergent, meaning that this expression is bounded. This integral from A to B of the absolute value of f of x dx, this thing, again, with the understanding that we're taking a limit for b, that this thing equals some value, some finite value. So if that's true, right, if we have that, then we have that the integral a to b of just f of x, not the absolute value of f of x, converges, and moreover, we can have this inequality here. As a footnote, this inequality isn't directly related to the rest of it, other than the fact that this result, meaning that this converges, lets this make sense, so I can write that with the absolute value. Otherwise, this is sort of its own little bit of a note, a footnote to the end of this proof. All right. So this seems almost trivial, and in fact, it sort of almost is, because remember we have that comparison test that told us that, so recall, if, let's say, f of x is less than g of x, less than or equal for every x, then if the f and g both Riemann integrable on A to B, well, sorry, I'm trying to do this the short way because I want to just recall it, but let me be careful and thorough. So, let's say f of x is less than g of x, and this is not quite everything. I'm going to come back to make an emphasis, so leave a little space around this if you're taking notes. Then if, so our comparison test said that if f of x is Riemann integrable from A to C for A less than or equal to C less than B, and g of x is in Riemann integrable of A to B, where I can sort of let this be the improper integral, then f of x is indeed in A to B. So this was the comparison test we talked about at the sort of very start of the improper integral, written a little differently, but pretty much the same idea. But the thing is that this wasn't quite it. If you remember, the thing that we had was that we needed, sort of for a silly reason, but we needed to make sure that it wasn't just bounded above, but bounded below as well. And so we added this 0 less than or equal to f of x. So this is really what it said, right? If f of x is a non-negative function and bounded by g, then we're good. So up here, we could think about taking, for example, g to being the absolute value, and we'd be fine, except there's nothing here saying, right, that f is a non-negative function. It could be that f is negative, and that's a problem, right? But at the same time, sort of conceptually, we might think, well, if f was unbounded below, then wouldn't the absolute value sort of flip that to be unbounded above and cause the problem? Meaning that even if it were going to some large negative number, this should somehow detect that fact and fail. So the fact that this doesn't fail means that it should still work, right? The intuition should tell us that it shouldn't make a difference that this is allowed to be negative, because the absolute value should sort of account for that in some way. And indeed, that is the right intuition. We just have to make it rigorous. So the way we do that, we say define g of x to be absolute value f of x. But again, this isn't quite enough because we want it to be sort of related to f, not absolute value of f. So we're going to subtract off f of x. So this means that if f is some positive thing, this is going to be 0. But if f is negative, I'm going to get positive minus the negative, which means I'm going to get sort of twice the positive value, meaning that this thing is less than or equal to 2 times f of x. But at the same time, this thing, g of x, you can think of this as being an upper bound on f. So if I take the upper bound and subtract off the value, this thing is indeed non-negative. Right? So for every x specifically in, A to B. And I'm just going to make a note here that this is Riemann integrable, right? That's what we were just saying, right? That's what it means for it to be absolutely convergent. And 2 times that's still going to be Riemann integrable, meaning that this thing is Riemann integrable on A to B. So I have G is Riemann integrable A to B, G is non-negative. So now, by the comparison test, by this result here, by the comparison test, we have that we have that this is Riemann integrable. Yeah, we have that this piece, f of x minus f of x equals g of x is Riemann integrable. In particular, we have if I just move these around a bit, f of x is going to be absolute value f of x, which we know is Riemann integrable, minus g of x, which we just said is Riemann integrable. So this is Riemann integrable on AB. Thus, this thing, since this is Riemann integrable, by definition that means, right, that this integral A to B of f of x dx converges. Now, the version of this theorem in the book leaves out a critical hypothesis that we are using here, which is this. This f is in the Riemann A to C for C greater than or equal to A, but less than B. I've used that here, but I have not drawn super special attention to it. In fact, that's a really good practice problem, possibly homework or exam problem, hint, hint. So try to figure out why that is needed, and in particular, try to see if you can come up with some sort of counterexample when you don't have that hypothesis, i.e. something where you have this function that is absolutely convergent, right? A to B, the absolute value works, but when you do A to B otherwise, right, if you do A to B here, it doesn't converge, okay? Last but not least, again, just noticing that in general, f of x is less than absolute value of the f of x, right? Non-absolute value less than that. Then if I take the absolute value of both sides, I'm going to keep that inequality. And so in particular, this thing is less than or equal to that thing just because this is allowing the positive negative area to cancel beforehand, whereas this is not. So this is just sort of a note that this holds. Okay. So this is also done in the book with the caveat that they sort of gloss over this very important hypothesis. So you can take a look at that as well. But again, I challenge you to come up with a counterexample where if you don't have that hypothesis, this theorem fails. Okay? And that is it.